COBOL is so old. How old is it, Johnny? COBOL is so old, it's older than that joke. You can mark in your calendar, this is the first recursive joke you ever heard. COBOL predates Bacchus-Naur form. COBOL is the only language written for data processing purposes, bespoke for that single reason. So I came here today to talk to you about that language, about how it came to be, about why it's so important still, even though it's a big secret to most people, and what we did to bring COBOL to GCC, to give us an open source COBOL compiler for the first time, and why we did that. COBOL is a gigantic infrastructure you've never seen. It is billions, maybe hundreds of billions of lines of code. You might ask yourself why that is. The reason is because for 3 decades, COBOL was the only way you wrote programs. If you were in charge, say, of a large company, and you had a once-in-a-lifetime opportunity to make enormous changes in your organization from an information management point of view, and they gave you one language and 3 decades and all the resources you could ever use, how many lines would you write? Every bank, every insurance company, every railroad has many millions of lines of code. We have a small project we're undertaking now to convert some COBOL. That small project is 19 million lines of code. They are vital lines of business. They are the programs that compute the interest on your savings account. They are, with 95% certainty, that your last ATM transaction went through a COBOL application. They were not written carefully. They were written in layers over time by a lot of people who weren't trained to write programs. They were written in the 1980s, and 70s, and even 60s for systems that IBM hasn't manufactured for 40 years. And they do that through running emulation. Your system expects to run on a system that was manufactured in 1975. You go to IBM, you say, can you emulate that system? And IBM says, absolutely. And you can have that for the low, low price of how much you got. So it's expensive. And it's entirely proprietary. And so we're trying to pry this out and put it on the open source radar. So I'm going to tell you a little bit about how it came to be true. The IBM 1401 came out in 1960, 59. Ask yourself, 16 kilobytes of memory, the first computer IBM made that was based on transistors, so you didn't have to use vacuum tubes to run your stuff. That's how old we're talking about. They offered 2 languages. You want to do science, you've got Fortran. You want to run it for your business, you've got COBOL. I failed to mention, they sold 10,000 of those computers, which in those days was a lot of computers. I'd like to sell 10,000 of what I got. The 360 was a revolutionary piece of technology. They called it 360 supposedly because it covered 360 points on the compass. Any kind of computing you want to do, you could run on this thing. You no longer had a machine specialized for science or a machine specialized for data processing. And it came with 3 languages. COBOL, Fortran, now PL1. The PL1 was supposed to be the thing that brought Fortran and COBOL together. I'm not sure that ever worked. 3/4 of all computers and computer programmers were running IBM stuff. Almost all of them in the business world were writing COBOL programs. It kept on going. And COBOL kept on being the thing. So if you wrote a COBOL program in 1965 or 1975 or 1985, you were good for good. You didn't need. Around this time, there's a story in Coders at Work, if you've read that book, where Fran Allen was at a forum a bit like this. Ken Thompson was presenting for the first time a new language called C. And she was from IBM, and she could not believe what she was seeing, not because she was impressed, that was not it, but because everything that they were doing with COBOL, with compilers generally, was the opposite of what our friends from Murray Hill were doing. COBOL is an all-encompassing language. I'm going to show you a little bit about why it covers everything you need to know. When I used to work with COBOL programmers, I thought they were stupid because I would say, how do you do X? And their answer always was, how do you do X in COBOL? It either exists in the language or it doesn't exist at all. This was an important feature of why it became such an important language. So we have almost every programmer in the world working on one platform, in one language. That's why we have billions of lines of COBOL still running today. And it wasn't only IBM. Their competitors emulated them too. So you could go to, I don't know, maybe not Univac, but certainly Digital Equipment or a number of other companies, Unisys, and you could, Unisys for sure. And you could get yourself a COBOL compiler. I remember recently I saw an interview by Michael Stonebreaker, talking about undertaking the possibility of bringing Ingress to the marketplace, the database, before it was commercialized, before it was common for college professors to start businesses. And the University of Arizona called him up and said, we're ready to go. We'd like to use this thing. Where's the COBOL interface? It was running on Unix. We don't have one. So that was the problem. I will say to you that there is no higher level language anywhere. There are a lot of languages. I haven't used one that's higher level than COBOL. The COBOL programmer is only expected to do one thing: read the input, do the work, put the output. There's no styling of the HTML. There is no consideration of the network technology. There's nothing. You just read and you write. It is the only record-oriented language, I'm going to say. The data is very definitely described. You do not deal with the OS at all. Everything you need to do is available inside the language. It's got immense error handling that is superior to anything I've seen anywhere else. You name me another language with 100 named exceptions. And the computation is designed to be exact. This is a typical, I'll say, record description. It's, I agree, old-fashioned. Who puts numbers in front of things now to put things where they belong, right? I don't, but it's how it's done. You'll see the first line, our multi-1, he's 9 bytes, 9 characters. They have to be numbers. And then implicitly, that V means that's where the decimal point goes. Well, I store the decimal point, it goes where the V goes. The compiler will take care of that part. And when we get to multi-3, that thing, when it gets displayed, is going to have a $sign in front of it. The next section there on line 276 shows how the records nest. In a moment, I'll show you why that's interesting. But we have character values there. There's spaces that take up space because it's on a disk someplace. It's going to have but we don't need to know what that is in this particular record, so it's just filler. In fact, the word filler doesn't even have to be there. It takes space because we say it has 31 bytes. So we're not working with a language where the compiler can decide where the bytes are going to align themselves. We're not worried about being able to shift this data structure across the network or onto a disk, onto another, because it'll always be where it's going to be. I'll come to hyphenation in a moment, but basically the important part, or what I think is interesting about this nested record structure, is that if you've named a piece of a record someplace anywhere, and it's unique in the whole program, you can just talk about it directly. You don't have to qualify it and say it's A of B of C of D. You just say, okay, so all of these, to get to end or desk, all of these variations are valid. The first one is valid because it's unique in the program, and the others are valid because those are superiors, those are parents of those of end or desk. I only know 2 languages that let you put a hyphen in a name, and I think hyphens in names are nice. I know Lisp does that, and COBOL does that. And I think the reason that no other languages don't do it is that they came after BNF. They came after Bacchus-Naur, they came after Algol, and every language looks like Algol. What you give up, if you say you can put a hyphen in a name, is you have to put spaces around dashes when you want to do subtraction. That's what you give up. That's all you do. A couple of white spaces. Me, I put spaces around my subtraction in C, so I recommend it. Record-oriented I/O means you just talk to the file. At the top of the program, you say, I've got a file. The file has this handle we're going to use to deal with IXFS1. Assigned to, that's the OS side. That might be a literal like I've given here. It could be something from the environment. There's a bunch of ways that you can pass the operating system's notion of a file into the program. But as far as the program is concerned, IXFS1 is the whole story. Not only is that the whole story, but it's got a key. It has a record definition. IXFS1 has a whole bunch of stuff about how it's organized on the disk or not. It doesn't have to be a lot of that stuff. But now we also have a whole record associated with it. Exactly what the layout of the record is going to be when I read that record. And the key is identified on line 525. It's good. We've said that's going to be the key. This is our job as the compiler writer now to implement all this to make sure that when you read this thing, you've got a key where you said you were going to put it. When we move something, when we write it to the disk, we're going to just we already identified we already know what records are associated with, what record layouts are associated with what files, so we don't have to say what file we're writing to. If we've got a record, we know where it goes. Where else could it go? It can't go anywhere else. It's defined to go with the file. And if it doesn't go there, well, we have conditional handling built right into the language. Again, the user, the programmer, doesn't have to understand what kinds of errors could occur. If there's an error, you can do something. In this case, we go to the right fail GF01 and we increase a counter or something. But the errors are built, it's expected there'll be errors, and there's a standard way to handle them. I think that's different from the way you do it in, say, Python, for example. We can say try and accept, but you have to know what you're accepting. Here, the exceptions that are going to be generated from the right are built into the compiler, built into the language. I gave a presentation at FOSDEM this year. The title was COBOL was the original safe language. And in there, I examined what C++ is doing these days about safety. And the sort of 2 top elements that have been identified as CVEs in C++ are dereferencing null pointers, referencing things after they were freed, writing past the end of the buffer. These are not features of COBOL. You cannot do those things in COBOL. We do, in fact, have pointers nowadays, but it's not typical. Normally, the simplest programs, all the data are statically defined. We know exactly how long the string is. We don't have any way to move something else. There's no string copy, so you can't write to some wrong place, and you can't write to some wrong length. You can only move things between things, and the compiler knows how long both of those are, so where would it go else? I/O is built into the language. We know whether the files are sequential or random. We know how big all the records are. Computation is based on, we don't always use decimal arithmetic, but exact definitions of how big the values are. Display is a COBOL verb. It turns out if you've got a COBOL variable and you say display, you get it. You don't have to say %s or %d or %f, or there's no interpretation necessary. It's going to display. You already said how you wanted it to be displayed when you defined the data in the first place. How many different ways do you want to display it? It's there. If you want to display it 2 ways, you can. You can move it. You can also redefine it. But it's all done for you. So no mojibaki, I don't know if you're familiar with that term, but that's when you splat something to a screen and it turns out that the encoding is not the one that the thing was expecting. No forever nodes. I love move corresponding. Why does no other language do this? We move one structure to another structure. Which things would you like moved? How would you like them done? Well, if you're in C++, I happen to know you can write a copy constructor and do all of that. Make sure everything goes where it's supposed to go. Eliminate the parts that don't matter. COBOL did that for you in the compiler. Here's 2 data structures with the elements in different orders. I didn't invent these names. They came from the NIST test suite, so I wanted you to see genuine COBOL, not something I came up with. And at the very bottom, move corresponding. 1 to 3. The compiler does this, just moves the things where they're supposed to go, according to the names. The names are important, right? Because the compiler knows about the data and how they're organized on the disk, the compiler can enforce things for you that the other languages can't. You cannot open for random access a file that is defined to be sequential. You just get an error. You can't read the wrong record size because it's all been defined for you at the top. I mentioned CICS here for the same reason, because a lot of us here have done web programming of one kind or another. I've done a little of that myself, not much. But the old system called basic mapping support, which has existed since, what, Marty? 1965, about right? 69. 69?
Yeah.
Basic mapping support defines the user interface. It defines the data structure that represents that user interface of the COBOL program. And does the COBOL program care about the user interface? It does not. The COBOL program reads the map. It is presented with the data structure, just exactly the one you want. Does whatever it does. Says, write the map. End of story. All the UI stuff happens on the other side. It's a little boring as a programmer, but you only have to know one thing. And I want you to ask yourself as you do your job, how many technologies do you need to do your job? How many things do you need to knit together to make it work? And why are we building giant masses of things of all this stuff to glue together and not a single system that unifies it so it's under your control and and the system that you're working with is taking care of those details for you? Most COBOL statements, like the write statement I showed you a moment ago and the multiply statement here, have what are known as a conditional form. That particular statement may raise certain errors. Your output from your multiply might be bigger than the variable you're putting it into. Your write statement might go to a file that's no longer there even, or failed for some other reason. The errors that that particular statement raises are recognized by the language and will raise and can be handled directly there in that, at that statement. And as I said, it's a little different from the way you do things in most exception handling situations where you have to understand where the program, it's up to the program to get right, what kinds of things can come back from what kinds of exceptions can be raised. Another feature is that there can be at the top of, not quite the top of the program, probably what they call the procedure division, you can have these things called declaratives. These are centralized error handlers. So you've got some global definition for how the errors will be handled. Here we've said anything that happens to our friend IXFS1, we add 1 to a condition. I don't know, not very important, but it is captured and recognized there. Declarative error handling is a big deal. The first form is an old one. It deals only with I/O issues, can be associated with a particular file or files, or with a particular mode of operation. The second one handles the other, I'll say 90 forms of exception conditions that are defined, where you name them where you can handle them by name, also associated with a file or not. To take an example, these are the size conditions, exception conditions that can be raised out of the 100 I mentioned. We've implemented 3 from this particular block. So if you divide by 0, you can have a thing at the top of your program that says 0 happened, that wasn't supposed to happen. Try that in your C compiler, see what happens. You probably won't even get a divide by 0 error anymore, because it's undefined behavior. We have exact computation. By definition, you can state how are we going to do rounding. I think if I was a bank, I would want to know. I used to work in quantitative research where rounding wasn't all that important. I didn't worry about it. But I think if I was computing interest, it would matter to me. So, record-oriented. The definition of the data is always known. You only work within the language. You never have to think about a different technology. Errors are managed by the statement or declaratively, and the computation is exactly what you want it to be. With all of that going for us, what's the problem? The problem is, it's not everything. For that to be true, other stuff has to exist. And other stuff doesn't exist in a lot of cases. And so that the whole mainframe architecture, it's a little tricky to transpose it onto a POSIX framework. So we have written the compiler, and we're proud of that, and we're glad for it, and we know it's a first step, but we also know it's only a first step. Because these other kinds of things, you might recognize their names, don't necessarily have good analogs or good replacements. Some do. So that is the trick. The trick is, yes, it's great to compile the program so we can run it on POSIX now, or Linux, but yeah, and now what? So to bring it back to you, the existing systems are very expensive because there's nowhere else to go. Those systems don't have a good reputation for how they interact with the rest of the world. So this kind of walled garden effect, which we've definitely been able to, within GCC, make better. The new systems are free, but there are parts that are missing. I'd like to talk about now how we came to do the GCC part and what GCC looks like from the inside a little bit. The Siemens company makes its living by open LDAP support. And I can recommend it if you have a use for that. We are made of refugees, most of us, from large companies, and so we know how the errors, or not the errors, the conditions under which people work in large firms. And we asked ourselves, could we write a COBOL compiler? We think so. Can we make money at it? Probably, maybe, we'll see. Either a little bit or a lot, we'll see. Either no or a lot. So we asked ourselves, how will we do this? There exists, in order to avoid confusion, I want to mention that there is another COBOL compiler, also sponsored by GNU, that I worked on for a while. But what the GNU COBOL compiler does, it's a creditable product. It's a working thing, but it's a transpiler. It produces C, and then you compile a C. We thought about GCC, we thought about Clang, we thought about picking up broken COBOL compilers that already exist. There's quite a few of those. We're starting our own and forgetting all of that and just writing a compiler from scratch. But GCC really stood out as the best answer. GCC has an established framework for adding new languages, and every few years a new one shows up. In 2025, that was us. They're terrific people, great people to work with, and because we're part of GCC, we get all of the features that are in GCC that we didn't add. We get direct support for GDB, obviously. That's tricky when you're doing transpiling. We get portability to, I don't know how many architectures. We care about a half a dozen. So what does GCC look like? GCC looks like this. In comes source code, out comes object code. Different kinds of source code have different processes they go through. Ours we call gcobol. Gcobol looks like this. Takes source code and produces assembler. We have command line options, we have the COBOL text. We'll go through, that's how that's, and something else happens on the other side. The assembler does work for us. So our little piece looks like this. We still have our own command line options, we still have the COBOL. Copybooks are the include files of COBOL. COBOL has two different recognized input formats. One's the old, one's based on the 80 column cards. So there's a transformation that happens, and it goes through things you might recognize through YAC and LEX, generating a giant abstract syntax tree, I think it might be called, which is in the form of a language that GCC calls generic. It goes into a code generation system, and then on the other side, assembler. What does that code generation system look like? Well, to me, it looks like that. You put it in, it comes out. Internally, it looks something like this, from what I understand. This is all the stuff we didn't have to write because we're just adding to GCC. So at the moment, if you are of a mind to use an open source COBOL compiler, you have two choices. You have one that's been around for a few decades and is quite effective. It has its limitations which let us undertake ours, but there's good reasons to use it and people do. In particular, the GNU COBOL project made a great effort to recognize the many different varieties of COBOL that exist. I told you there's only one language. It's true, but it's got flavors. We, on the other hand, are now an overnight success, and we emulate a couple of dialects. Specifically, we want to make sure we can compile IBM's version of COBOL. There's another fairly popular, smaller COBOL compiler from a company called Microfocus, now Rocket, and it's popular enough that we need to make concessions in their direction. But we used for ourselves the ISO definition of COBOL. How fast it goes depends on us. We're learning that every day. And because we're built right into GCC, the GDB side works right away. So right now today you can download a compiler, our version of GDB, and you have source code debugging in COBOL. The easiest way to decide what to do is to let people tell us. So people are trying out the compiler, they come to me and they say, this, that, the other, it doesn't work. There's a lot to do. In particular, I've just named a couple of these things, but XML support's a funny thing. Here you would like to be able to read an XML file and write to something else, or read something else and write to XML. You can do that today with a variety of technologies. I'm sure you use different things, but this is another example of put it in the compiler, then it just works. And you have to think about anything else. And they came to us, they mentioned that specifically. They said, I can get 3 engineers, but when it doesn't work, then I'm not sure where the problem is. Put it in the compiler, work there. COBOL is running the books and records of almost every firm you know. GCC now has the first free direct COBOL compiler. I think next year when I come here, I'll be able to tell you who did this and why it's being used successfully. I'd like to think so. There's plenty of more work to do. And where it goes, that's for us to decide. That is my presentation.